angular momentum. And the component of L, the Z component of the angular momentum is m and h bar. Right, so now m we know from early session, and I just, to repeat, I just said a bit before, ranges between -L and +L. So m is greater or equal to -L, and go up by integers, and is less or equal to L. So it takes 2 little l plus 1 possible values. Alright? So I'm going to risk falling off the edge of the bed. So if I'm conscious of it, maybe I don't need the stool anymore. Alright. So so here's what I've just been saying. Now from the from the expectation values, the expectation of L squared cannot be smaller, it's common sense, than the expectation value of the Z component, because the L squared is Lx squared plus Ly squared plus Lz squared, right? So, and they're all squared, so it has to be larger than just one of those three components. So, and from that, this is Lz squared expectation value. It'll be m squared, and L squared. This is the expectation value of L squared. Okay? And so m squared must be less than L times L plus 1. We've done this before, right? We actually in using the expectation values of L squared and Lz squared. Right. So looking at it visually, if these vectors here, state vectors if you like, if they represent the angular momentum L, and your z-axis is vertical, let's say, and we know these m's here, they are the eigenvalues, they are the allowed discrete or quantized values, eigenvalues of the z component of the angular momentum. Right? And if L is 1, then m will have three possible values, -1, 0, +1. And if L is 2, m will have 2L plus 1, so that's 5. Right? So -2, -1, 0, 1, 2, and if L is 3, so 2 L's plus 1, so that's 7. Right? So m can have 7 possible values. So z-axis going this way, and m, remember, is the component of the angular momentum. So the angular momentum is sort of the possible orientations of your angular momentum L is quantized. Okay? Now you may say, well, what is this Z? In physical terms, what does that mean? Well, it will depend on your measurement. Depends how you're measuring it. Like if you're trying to measure the angular momentum component, you'll probably have to put it through some kind of magnet or something, and the orientation of the magnetic field will define what Z is. So a famous experiment was done. Let me just check. It's the Stern, S-T-E-R-N, which is a German word, a physicist, that means star. Let me just Stern Gerlach, and Gerlach, another German guy, collaborator. Let's just see if it's in the text. S-T, Stern Gerlach. No, surprisingly. All right. Well, let's see if it's in the M1 level. Stern Gerlach. S-T. Yes, good. Stern Gerlach. Okay, so in the M1, the first year master's level course, we'll talk about the famous Stern Gerlach, G-E-R-L-A-C-H experiment, where I think it was ionized silver atoms were shot through a very inhomogeneous magnetic field, and so the orientation of that magnetic field determined the z-axis, and relative to that z-axis, these ions, the angular momentum obeyed these conditions. So I'm a little surprised. It's such a famous experiment that it's not mentioned in Davies' text. Well, no matter. I mean, a general point. I have dozens of texts in quantum mechanics and many others, and if I live long enough, I may have time to do what I call repeats. That's lecture set, a whole course on a different text on a topic that I've done before. So I may loop back and use different textbooks on the same course, for say undergrad level quantum mechanics or M1 level quantum mechanics. And you do notice that different authors emphasize different things. That's not surprising, So you get a broader perspective if you study any field from the context of different authors. You realize that it's not black and white. It's fuzzy. What some people consider important, others neglect, and vice versa, and so on. Okay. Anyway, so so the angular momentum then, L, like L hat, its orientation relative to the z-axis, and the z-axis will depend on, how do you define what z-axis is? That will depend on your strategy of measurement, how you go about measuring it. Like it might be a strong magnetic field this way, or whatever. Okay, so the angular momentum will be oriented relative to that z-axis in 2L. Little l is one of the that comes out of the eigenvalue for the momentum. Okay, so there'll be 2L plus 1 possible orientations of the angular momentum relative to your z-axis. Okay, and for L1 you have 3 possible orientations, and for L2 you'll have 5, and L3 7, and so on. Now, I've sort of cut it off the bottom here, but using the correspondence principle, which we've talked about quite a few times, when you get to human level scale, the angular momentum is human scale objects. The angular momentum is so huge that the value of L, remember the eigenvalues for the angular momentum squared are little l times L plus 1. Well, if your angular momentum is so large, little l also has to be huge, and so that means you've got a huge number of orientations. Now you only got 180 degrees. If you've got a huge number of possible orientations, the difference, the delta of the small change in the angle of these discrete orientations of the angular momentum relative to the z-axis, they get so tiny that effectively they're continuous. Right? So you get the typical correspondence principle reasoning. You merge then into classical thinking, where the angular momentum is effectively continuous. Okay, right? Well, that's the end of this session, and I did not fall off the end of the bed, so maybe I'll keep doing this from now on and not use the little stool. So maybe a blessing in disguise until I fall off again.